When we make up a solution, there are two major parts. There's the solute and the solvent. Okay, so the solute is something that you dissolve, a substance that you dissolve in another. And this substance can be a gas, it can be a liquid, it can even be a solid. The solvent is a substance of larger quantity that the solute dissolves in. So really the definition of solute and solvent is more about how much of each item there is rather than something more detailed than that. So typically our solvent is water, but it certainly doesn't have to be. And the solute could be something like an ionic compound that gets dissolved. I didn't write the word dissolved. That gets dissolved, or it could be something like sugar, or it could be a gas that's dissolved. All right, but when we talk about how much solute is in the solvent, we need a unit of concentration. And the unit we will use most of the time is molarity, which is designated capital M, and that is moles of solute in a liter of solution. Okay, so I want you to note that it's not in a liter of solvent. So the concentration is per liter of entire solution. Okay, what difference does it make? Well, let's look at an example. Let's say we have a 2-liter container with a line at 2 liters, and we take 2.5 moles of sugar, and we put them in the flask. And we want to make a solution, we will add water up to the mark. Okay, so we don't add 2 liters of water to make the solution, we add water up to 2 liters to make our solution. All right, so then we add water up to the line, up to 2-liter mark. Okay, so then the concentration would be 2.5 moles of sugar, because that is our moles of solute. Sugar's our solute. And it's per 2 liters of solution. All right, and let's say that we're doing it with 3 sig figs. Let's say it's 2.00 liters of solution. Then we can calculate that we have 1.25 molar sugar solution. All right, so if we want to make solutions from a solid, we need to know the molar mass of the solute. Okay, so if it's a solid, that will be in grams per mole. And if we multiply that by the molarity of the solute that we want, and times the volume of the solution that we want, we can then calculate how many grams we need to make that solution. Okay, so for example, let's say that we want 100 milliliters of 0.05 molar KCl. Right, how do we make that solution? Well, we first figure out the molar mass of KCl, which is, for potassium, it's 39.10 grams per mole, and for chlorine, it's 35.45 grams per mole. So our molar mass is 74.55 grams per mole. All right, we use that number for the molar mass. .55 grams per mole. Multiply it by the molarity we want, 0.05 Now let's make it 0.050 for sig figs molar. So we'll say we want 0.050 there. And then the volume is, we do it in liters because molarity is in moles per liter. So to make the units cancel, we have to make that into liters. And we can calculate that we need 0.37 grams of KCl to make that solution. All right, diluting. When you dilute something, you don't change the number of moles. If you have strong coffee and it's too strong for you and you dilute it with extra water, you're not changing the total amount of coffee you drink. You're just changing how concentrated it is. So for dilutions, we make a dilution calculation saying that the number of moles of solute do not change when you dilute it. So the molarity of the dilute solution times the volume of the dilute solution will be the same as the molarity of the concentrated solution times the volume of the concentrated solution. And the reason for that is that molarity times volume is moles. So this is moles after dilution on this side of the equation, and it's moles before dilution on the other side. So the concentrated is the one before, and then you add water and you dilute it, or you add solvent and you dilute it. All right, so we can use this equation to calculate amounts involved in dilutions. All right, so let's do a sample calculation. We want to prepare 750 milliliters of 0.8543 molar copper nitrate from a stock solution of 2.050 molar copper nitrate. All right, so let's make it just D instead of the whole word dilute. So MV for the dilute solution is going to equal M times V for the concentrated solution. All right, so what do we know? The dilute solution we want is the one we want to prepare. Okay, so this is the dilute. So the molarity of the dilute solution is 0.8543 molar. The volume, remember to make it in liters because molarity is in moles per liter. And the stock solution, the concentrated solution, is 2.050 molar. The one we don't know is how much volume of the concentrated solution we need. So then we can solve. For this, we can divide both sides by 2.05, and then we will get the concentrated volume that we need is 0.3125 liters, or 312.5 milliliters. All right, try one for yourself. This time you're solving for a different variable. 40 milliliters of 3.00 molar HCl is diluted to 100 milliliters. What's the new concentration of HCl? Go ahead and stop the video and try that. Again, MdVd equals McVc. Sometimes people say M1V1 equals M2V2. No difference. Okay, the molarity of the dilute solution is the new concentration. We don't know it. That's what we're going to solve for. The volume of the new solution is 100 milliliters because we start with this concentrated and we dilute it to this volume. So it's 0.1 liters. And the concentrated solution is 3 molar. And the volume is 0.040 milliliters, but 0.040 liters. So the molarity of the dilute solution when we solve is 1.2 molar. Okay, more on solution. So let's revisit concentrations in molarity. It's moles solute per liter of solution. M times V gives a number of moles. So for any situation, molarity times volume in one case is going to equal molarity times volume in the second case, as long as you haven't, you're just diluting. As long as you're diluting, that'll work. All right, now we can look at solution stoichiometry. In other words, doing calculations using reaction equations involving solutions. So if we have amounts given in molarities and volumes, we know how to calculate moles. right? Because molarity times volume is moles. So we can use that, and remember that when we work with reaction equations, we need it in moles. Okay, we need it in moles. So if we're working with solutions, we can get it to moles by multiplying molarity times volume. All right, let's try this sample. We have a reaction equation, and we're asking how many grams of oxygen, the product, are formed from the reaction of 200 milliliters of 3.0 molar H2O2, hydrogen peroxide. Okay, so we have an amount of reactant given in volume and molarity. So remember that we always need to convert to moles in order to use a reaction equation. So we'll do that. Convert to moles by doing molarity times volume first. Okay, so 3.0 molar, which again is moles per liter, but I'll write it as molar, times 0.2 liters. Okay, and that gives us moles. Whoops, didn't want that. So that is converting to moles. And then we're simply, now that we have it in moles, we do reactions the same way we did for when we had it in grams. Okay, then we use the mole ratio, 1 mole of oxygen per 2 moles of hydrogen peroxide. And then we want the answer in grams, so we can convert oxygen back to grams by using its molar mass. And when we cancel the units, we get 9.6 grams of oxygen. So solutions just provide another way to calculate moles and use them in reaction equations. Okay, another thing we do with solutions is we perform titrations. A titration is where you determine an unknown concentration of something, and this symbol means concentration. And we determine that concentration by reaction of a known amount of another reactant. Okay, this is often used with acids and bases. Whoops. We will see another type of titration as well, but acids and bases are one type of titration. All right, and the concept of the equivalence point is when the moles of acid are equal to the moles of base. And by that I mean, by acid I mean H plus, and by base I mean OH minus. And we use something called an indicator to tell us when we've gotten close to the equivalence point. An indicator is simply something that changes color at an appropriate acidity level. So we can tell we've gotten close to our equivalence point because the color changes. One common indicator is phenolphthalein, which turns pink when it's basic. All right, so let's look at an example reaction. An acid, HCl, hydrochloric acid, will react with a base, sodium hydroxide. Okay, and HCl provides a source of H+. Sodium hydroxide provides a source of OH-. That makes them an acid and base. And the H+ and OH- become water, and the leftovers are sodium chloride. All right, but what we do is we often add a known amount of one of the reactants to an unknown concentration of the other one. So for instance, let's do it, let's say that we have an unknown amount of HCl, and we have an HCl solution, okay, which means it's aqueous, in the container below. And we have sodium hydroxide, the base, in a burette which is a graduated tube that will allow us to dispense the liquid, and it's at a known concentration. HCl is at an unknown concentration. And we add the base drop by drop to the HCl until we see a color change, and at that point we know that the number of moles of OH minus equals the number of moles of H plus. So let's do a calculation for titrations. A titration takes 67 milliliters of 0.880 molar sodium hydroxide to neutralize 100 milliliters of HCl solution. What was the concentration of HCl? Okay, so here's the same reaction I just showed, and we know that at the equivalence point, the number of moles of H plus will equal the number of moles of OH minus. Okay, so in this case, you get 1 mole of H plus for every mole of HCl. So we simply say the molarity times the volume of the acid, and we get 1 mole of OH minus for every 1 mole of sodium hydroxide. So we have the molarity of the base times the volume of the base. And this is because they are 1-to-1 ratio between the ions and what they came from. Okay, so what we don't know is the concentration of HCl. That's the molarity of the acid. So that's our unknown. The volume of the unknown is 100 milliliters. The molarity of the base was 0.880, and the volume was 0.067 liters. So we can solve for our molarity and get 0.590 molar HCl for the concentration. Okay, so now you try one. Let's say that a 300 milliliter solution of sodium hydroxide spilled. And in order to neutralize that sodium hydroxide, in other words, in order to provide enough H plus to react with it, you needed 440 milliliters of 0.1 molar HCl. What was the original concentration of sodium hydroxide? Okay, so this is kind of a backwards titration compared to what I just did. This time you have an unknown amount of base and you have a known concentration of acid. So go ahead and do the calculation yourself. We can say that the moles of H plus equals the moles of OH minus when we have neutralized it. And the moles of H plus, again for this case, are the molarity times the volume, because we get 1 H plus for every HCl. And for the base, the molarity of the base times the volume of the base equals the number of moles, because we have 1 OH minus for every sodium hydroxide. Alright, so the molarity of the acid is 0.1. And we're pretending there's another sig fig there. Alright, and the volume of the acid is 440 milliliters, so that's 0.440 liters. What we don't know is the molarity of the base, but we do know how much volume spilled, which was 300 milliliters. Okay, so solve for the molarity of the base, and you will get 0.15 molar.